Problem number 49, 44. We're given triangle, and we have to prove that perpendiculars erected at the midpoints of the sides of this triangle meet in the same point. I have sketched here a triangle ABC, and what we can do here as the first step is to build, well, let's say arbitrary point B, which is supposed to be the intersection of these lines. What we can do first is to draw a line L1 such that L1 is perpendicular to AC, and let L1 intersect AC in point H1. This is possible. It doesn't contradict the Euclidean geometry. We can absolutely do this. This is going to be point H1. Well, honestly, this is not the best triangle possible here because of the proportion of the sides. Let me make another triangle to make it more easier to understand and easier to draw these lines. This one should be better. H1, A, B, C, H1. Here are another points. We don't know what these points are about yet. So we are kind of making this line here. This is perpendicular. And H1, let H1 be such that H1 equals H1C. That's also possible because we choose what H1 point is about. We choose what kind of point it is. We just selected the point in the line AC such that H1 equals H1C. That's up to us which kind of point we would like to use for intersection. Now we can use the second line. We can use the line, draw line L2. And this line L2 would cross the line BC at point H2. Because again, we can choose the point H2. It's up to us to decide which point to use here at the intersection, such that L2 intersect BC at point H2. And we can also say that H2 perpendicular to BC, because we decided that, and H2 B equals H2C. So we are gonna have another line here, like this one. And let me just make this as a solid line here and here. That looks much better. Let point B, we know that these two lines have at least one point in common, and at most they coincide based on the axioms of Euclidean geometry. So let point B to be the point of intersection between these two lines, L1 and L2. This is gonna be point P, such that point P has coordinates x and y. Also, let's denote coordinates of A as x1 and y1, B as x2 and y2, and C as x3 and y3. Now, and this is completely possible, we can drop PH3 on AB such that H3 is the midpoint of AB. This is possible because we can connect two arbitrary points on the plane, again, based and according to the axioms of Euclidean geometry. So what is left to do here is just prove that our PH3 is orthogonal or perpendicular to AB. Because this is exactly the same thing. We constructed everything. What is left to do is just to prove that PH3 is perpendicular to AB because it is already midpoint and everything else matches, and it looks completely aligned with the requirements of our problem, except this one minor detail, except the detail that PH3 is not yet perpendicular to AB. So that's what we're going to do. And so my approach to this problem is relying on vector algebra. Since I already designated the coordinates of A, B, and C, you might have implied that I'd be using here the approach, or I'll be relying on vector algebra. I'll be using the vectors in order to prove that. We can actually see that given that H1 and H2 and H3, they are midpoints of AC and BC, we can find the coordinates of these points. That's the coordinate of H1, of the point H1 is x1 plus x3 over 2, y1 plus y3 over 2, H2 is x3, x2, x3, x2, doesn't matter, x3 over 2, y2 plus y3 over 2. Same for H3 is, it's kind of x1 plus x2 over 2, and then y1 plus y2 over 2. There is a well-known fact that the midpoint of between two coordinates x1 and x3, it is actually the half sum of these coordinates, and the same applies for y's. I'm not going to prove this fact here. I'm just going to use it as is. We also know that point P has coordinates x and y, and we know that PH2 vector perpendicular orthogonal to BC and PH1 is perpendicular orthogonal to vector AC. From this step it follows that PH2 inner product BC equals PH1 inner product AC, which is equivalent to 0. Again, this is a well-known fact that orthogonal vectors, they typically have the inner product of 0 in the Euclidean space, at least. So this lets us conclude, this kind of leads us to the following equation. We can conclude that since its orthogonal product is 0, and vector BC is essentially x3 minus x2, y3 minus y2, while AC is x3 minus x1, y3 minus y1, and we can do the same type of thing for PH2 and PH1 vectors. Just find the components of these vectors. What are the components of vectors PH2, for example? So this is x2 plus x3 over 2 minus x, y2 plus y3 over 2 minus y, and the same for PH1. This is x1 plus x3 over 2 minus x, y1 plus y3 over 2 minus y. Nice. Now we can move to the next equation, which is essentially the product of corresponding components of these vectors, which is the dot product, which gives us x3 minus x2 times x3 plus x2 over 2 minus x, right, plus x3 minus y3 minus y2, y3 plus y2 over 2 minus y equals 0. And then x3 minus x1, x3 plus x1 over 2 minus x, plus y3 minus y1, y3 plus y1 over 2 minus y equals 0. Now we can subtract from the first equation, the second equation. And for x, we're going to have x3 minus x2, x3 plus x2 over 2 minus x, minus x3 minus x1 times x3 plus x1 over 2 minus x, which gives us 1 over 2 x3 square minus x2 square minus x3 square minus x1 square plus, well, let's say minus x3 minus x2 plus x3 minus x1, which is the same as 1 over 2 these two terms cancel each other, and then we have x1, I guess x1 square minus x2 square. Again, these two terms cancel each other. We're going to factor out minus x, negative x, and then we have x1 minus x2. Then we can simplify that further, which is x1 minus x2, which is 1 over 2, x1 plus x2 minus x. We can do the same thing for y. Let's do the same trick. y3 minus y2, y3 plus y2 over 2 minus y, minus y3 minus y1, y3 plus y1 over 2 minus y, which is the same as y1 minus y2, 1 over 2, y1 plus y2 minus y. And we know that since we're subtracting from 0, 0, we're getting 0 as a result of their differences. Is there a difference here? So that apparently gives us x1 minus x2, 1 over x1 plus x2 minus x, plus y1 minus y2, 1 over y1 plus y2 minus y equals 0. And now here where the things start to click, because now we have, based on what we found before, we have that the coordinates of point h3 is x1 plus x2 divided by 2, and the same from y. And here it is. This is exactly our coordinates of h. And if we subtract y, that would give us the coordinates of the vector p h3. It is 1 over x1 plus x2 minus x, and 1 over y1, y2 minus y. And x1 minus x2, y1, y minus y2, this is the coordinates of vector AB. To be more accurate, BA. But it doesn't matter here, right? So BA from, yes, x1 minus x2, y1 minus y2. And based on this product, based on this sum that we had above, like it equals 0, that means that their inner product of these two vectors that equals 0, which is equivalent of saying that ph3 is orthogonal to vector BA. AB vector, BA vector, whatever, it is kind of orthogonal to the vector ph3. And this is the exact requirement of our problem. We basically proved that these two sides, they are orthogonal. That means the the perpendiculars which were erected at all midpoints of this triangle, they indeed match or intersect at the same point P. And so this is the problem for today's video.